Namely, I want to introduce notions of even and oddness, intervals of increase, decrease, turning points, maximum, minima, local behavior. Those are the things in this test. We'll see how much ground I actually cover. So let's start with the words even and odd. So if I say this function is even, how many people have heard the word even in the context of a function before? Good. How many people remember what it means for a function to be even? What does it mean for a function to be even?
Doesn't it mean both arrows are pointing upward?
Not necessarily. They might both be pointing downwards. They should certainly they should have the same behavior on either side. Yeah.
Wouldn't it be symmetry across the y-axis?
Yeah. So there's the graphical definition of even. A function is even in terms of its graph if its graph is symmetric over the y-axis. So you should be able to take the graph, flip it over the y-axis, you should get the exact same object. So let's just do a quick check. Here's the y-axis. If you take that graph and you want to reflect it over the y-axis, would you get the exact same thing again? I guess it's hard to tell with super precision based on just a picture of this resolution, but yeah, it looks like. This piece would wind up reflecting over there. This would wind up reflecting over there. Points on the graph would go to different points on the graph. How about this function? Is that symmetric over the y-axis?
No.
No, because, well, you can draw what happens when you flip it. So that means this one is even. This function is not even. And this third function, does it admit symmetry over the y-axis?
No.
There's an analytic definition of evenness, which is modeled after things like x squared. And maybe we can start with this graphical notion. So symmetric over the y-axis, that means that if I take a point on the graph and flip it over the y-axis, I should get a new point on the graph. But what does flipping a point over the y-axis do to its xy coordinate? Yeah.
Just changes the x value to negative.
Changes the x value to negative, or I guess positive if it was already. Yeah. So that means that if I start with a point x comma y on the graph, minus x comma y should be on the graph. Remember, y is supposed to be the function value, though. So that means,
Can you slide it
yeah.
down?
So f of negative x is the y value corresponding to negative x, but that has to be the same as the y value corresponding to x. So f of negative x is always the same thing as f of x. That's what it means for a function to be even. That seems familiar to everyone, I hope? Rings bells, even if you didn't remember beforehand? So if that's what it means for a function to be even, what should it mean for a function to be odd? Say that louder.
It does not have symmetry over the y-axis.
Not quite. So that's what it means for it not to be even. But that doesn't mean it's odd. Odd means something else. Yeah.
Is it where f of x is equal to negative f of x?
Yeah. You left out one negative sign. No, you said everything correctly. F of negative x is equal to negative f of x. Yeah, that's what you said?
Yeah.
Okay. Yeah, then you're right. So there's what it means for a function to be odd. Or if you prefer to have all of your negative signs on the same side, or negative f of negative x is the same thing as f of x. Right. It's clear that those two things mean the same.
Yes.
So let's think about what that means. So that means if I take the y value corresponding to negative x, it's the same thing as exactly opposite the y value corresponding to x. So if I take the x's and make them negative, I also make the y's negative. So if I, so if x comma y is on the graph, then negative x, negative y is on the graph. And let's just draw a picture of what that does. So if there's some point x comma y, then there's negative x, negative y. So if there were some graph going on up here, the same thing would be going on down there. What sort of symmetry is this? Yeah,
The origin.
yeah, it's symmetric over the origin. Its graph is symmetric over the origin. So if I take points on the graph and I reflect them directly over the origin, I'll get new points on the graph. Or maybe said a different way. Rotation by 180 degrees over the origin resolves the graph. And as a check, let's just see if each of these have that. So if you take this and you reflect it over the origin, do you get the same graph back? Folks for yes? Folks for no? Okay, cool. Didn't see enough hands. So let's reflect it over the origin and see what happens. And I'll reflect it over the origin two different ways. So here's one way. So I need to take each point on the graph, and I'll push it directly over the origin to get a new point. And I'll do that for all of the points on the graph. Eventually I'll wind up with something like this. Is that the same graph as you started with?
No.
No, it's a new graph. So is this function odd? No. Here's another way to get the reflection over the origin. Rotate 180 degrees over the origin. And that's handy because I can actually do that. I can pin the origin down. You remember what that graph looks like? I can rotate by 180 degrees. Do I get the exact same graph again?
No.
No. So this is even and not odd. How about this function? It was not even. Is it odd?
Yes.
Yeah. Take this graph, pin down the origin, remember what it looks like, rotate by 180 degrees. Do you get the exact same graph again?
Yes.
Yeah. Alternately, we've already reflected over the y-axis. If we now reflect over the x-axis, so there was the reflection over the y-axis, then the x-axis. Do we get the exact same graph again?
Yes.
Yeah. Doing those two reflections is the same as reflecting over the origin. This last graph, is it odd? So it's possible to be even but not odd, to be odd but not even, to be neither even nor odd. Do you think it's possible to be both even and odd?
No.
That's like I'm not going to tell you. Well, I am going to tell you the answer. How many people think yes? It is possible. How many people think no? It's not possible. Those of you who think it is possible, do you have an example in mind?
Yeah. Circle.
Ah, is that the graph of a function though?
Wait, no.
Do you want to change your vote? There is a single function which is simultaneously even and odd. There is exactly one. I will let you puzzle on exactly what it is on your own time. It's not a challenge problem or anything, but I think it's a satisfying answer to find. Think about it in terms of those equalities. if you notice it in the middle of class, go ahead and shout it out. So here are some functions. Let's use the analytic definition to decide whether they're even or odd. So here's a function, x squared minus 1. Well, I told you there's exactly one function that is both even and odd. Probably it's not this one. How many people think it's more likely to be even than odd? Okay, how many people think it's more likely to be odd than even? Okay, so since we think it's more likely to be even, let's check for that first. Let's see if this is even using this definition. So that means I need to see if f of negative x is the same thing as f of x. So let's do that. So f of negative x just means you replace all the x's with negative x's. What'll you get? You'll get negative x quantity squared minus 1. And now let's just simplify that down. What is negative x squared the same as? X squared. Negative x times negative x is the same thing as x times x. The negatives cancel. Is that the same as f of x? So this sucker is even. If I want to check whether it's odd, well, I'll need to evaluate negative f of negative x and see what I get. So that'll be negative x, lots of parentheses, squared minus 1, close parentheses. You simplify that down all the way, what do you get? Something like that. Is that the same thing as f of x? So is it odd? Not odd. G of x. What do you think? Is it more likely to be even or odd? Folks for even? Everything is more likely to be odd. Great. Let's check for odd. If it turns out to be odd, then I won't bother checking for even. So let's see if g of x is odd. So that means I need to see if negative g of negative x is the same thing as g of x. Let's do it. So I'll keep track of that negative sign. Now I'll replace all the x's with negative x's. Negative x cubed minus negative x. And let's see, show of hands. How many people want me to talk through the algebra to simplify? Okay, I will talk through the algebra simplification. Some of you might already be done. Let's start with this. Negative x cubed. That's negative x times negative x times negative x. So 2 of the negatives will cancel, leaving just 1 negative sign. So I'll leave the negative sign on the outside alone for now. That'll give me negative x cubed minus negative x, so plus x. Everyone with me so far? What's a bit of simplification that you would want to do next when seeing this? Yeah.
Distribute the negative on the outside.
Yeah, there's a distributive law for minus signs. So that'll give me negative x cubed, also known as x cubed, minus positive x. Is that the same thing as g of x? So is it odd? Cool. People feel okay about that? H of x. How many people think it's likely to be even? Odd? Neither. Both? Okay. Let's check. Odd seemed like the popular one, so let's see if it's odd. So in order to see if it's odd, I need to compute negative h of negative x and see what I get. And this will be exactly the same process as what happened right above. It'll be negative for that negative sign. Then replace all the x's with negative x's. Negative x cubed minus 1, close parentheses. And now I think I'm just going to be quiet for a second. And you guys will tell me whether you wind up getting the exact same thing as h of x. Let's see, so is it odd? Not odd? You simplify it out all the way, I think you wind up getting, oh goodness, x cubed plus 1, which is not the same thing as h of x. This is not odd. Do you think it's likely to be even then? It's also not even. And if I had told you in advance that that is the graph of y equals h of x, then you would have been able to tell me that much more quickly. How do people feel? Those ideas seem okay? Here's one last function. Y equal to sine of x, which is a function that will occupy us for much of the second half of the semester. How many people have already seen trigonometry? Oh, okay. Well, without even knowing that, look at that graph. Is that function even? Folks for yes. Folks for no. Cool. None of the hands went up at all. So take this graph, and I'm going to reflect it over the y-axis. So this hump will become a hump over here. Oh wait, does that mean the function changed? Is this function odd? Folks for yes? Oh, yeah. Folks for no? All right. So let's check. So internalize that graph. So I think just keep that in your mind. I'll fix the origin. I'll rotate by 180 degrees. Is that the same graph again? So is this function odd? It is. How many people have managed to come up with the unique function which is simultaneously even and odd? Okay.
Oh, is it horizontal line on, at 0, so y is 0?
Yeah. It is the line which is always 0. And now that you know the answer, like, you can check those conditions, right? Does it satisfy everything? Yeah. So the next thing that I want to introduce is something which will seem very intuitive, and that's intervals of increase and decrease. So here is the graph of a function. The function happens to be x cubed minus 4x. And so let's try to answer this question. Over what intervals is this function increasing? And I'm going to assume that you already know how to answer this question, because let's just answer it as a yes-no question. At that point, is the function increasing?
Yes.
Yeah. So that means that at that x value, the function is increasing. So let's just shade in the values that are increasing. Then we'll write it down in interval notation. So it's increasing right there. It's increasing all the way to the beginning at y equals -2. It looks like it's increasing, it's increasing, it's increasing until it changes at some point. What x value does that look like it has?
-1.
1.
Sure.
Ish.
-1-ish. Looks like it's a little bit more negative than -1. Time permitting, I'll go through some strategies to get better estimates by looking at graphs with the aid of a computer. So, it looks like it's increasing all the way from x equals -2 to x equals -1. And now, well, I guess I should decide whether to include or exclude -1. How many people would want to include -1? How many people would want to exclude -1? I was not expecting that to be so one-sided. So at -1, it certainly looks like the slope of the line at -1 is like 0. But if you take all the way up to -1 and include it, that's still, like, it's always increasing that whole time. So I guess what my takeaway is because there's a philosophy whereby you would include it or exclude it, as long as your answers are consistent across your exams to a single philosophy, I'll be happy. So let's exclude. So it's increasing from -2 to -1. So that must mean that at -1 it starts decreasing. And if you're going to exclude -1 there, you better exclude it now too. It's decreasing from -1 until what x value?
1-ish.
1-ish. And in fact, those two x values, there's one thing I can definitely say, they should be the same. Because if you look at this function, is that odd? Yeah, it is. So that means that this peak has to be the same as that bottom. So whatever the other x value is, it has to be the same. Decreasing from -1 to 1. And then it must be increasing then from 1 all the way to 2. That seemed pretty okay. And here's another easy question. If I were to ask you, where does this function turn around, what would you tell me? Well, it looks like at around x equals 1 and around x equals -1. The function goes from increasing, turns around, and starts decreasing. So at x equals -1, the function turns from increasing to decreasing. At x equals 1, well, maybe I don't have space. The opposite happens. All right, so now I'm just going to write down some formalisms. You already apparently have an intuitive idea. Question? Okay. You already have an intuitive idea what increasing and decreasing should mean. I think I just want to write out that definition formally. So, on the one hand, what should it mean to be increasing? It means somehow as x values go up, so do y values. Right, as x goes left to right, y goes up. That's what it should mean to be increasing. Similarly, what does it mean for a function to be decreasing? And I'm giving myself more space because I want to write a second version of that definition. What does it mean for a function to be decreasing as x values go up, y values go down? Said maybe a different, more formal way, if x1 is less than x2, if this x value is bigger than that x value, then f of x1, that y value, is less than f of x2. That seem reasonable? If you have an increasing function and you have two inputs that one of them is bigger than the other, then the outputs are going to satisfy the same inequality. If you have a decreasing function, then you can write it the same way. If x1 is less than x2, then f of x1 is greater than f of x2. What is the turning point? Well, you already know that too. The turning point is a point where a function changes from increasing to decreasing, or conversely. Cool. So based on the graph that's just above, what are the x values of the turning points for that function?
X equals -1, x equals 1.
Yeah, exactly. Turning points are at x approximately plus or minus 1. And one thing that I really should have done had I pre-planned correctly, this shouldn't take long to log in. So the next thing that theoretically I want to do is just demo how to use a computer graphing tool to get better estimates. And I think I'm going to hold off on that just for a minute. Oh no, it's going fast. Okay, cool. So if you had some sort of computer graphing tool, how would you want to estimate where those turning points are to as much precision as you want?
Graph it on
Yeah, graph it and then use that to get an estimate for where they are. If you like, we already had that on paper. But you can zoom in, get smaller and smaller viewing windows for more and more precise information. Yeah.
You can do the maximums and minimums of the words of the graph.
Yeah, so a lot of computer tools will also allow you to find local maxima and minima at the touch of a button. And those are the same as turning points. So there's also that option if you have a thing that can do local maxima on its own. Instead of doing that, I think that I'm going to stick with the zooming in, at least for the live demo, because that's something that I think feels more approachable. If you have a maximum button, it'll do the job. So let's do it. Let's plot x cubed minus 4x. There it is, over a bigger viewing window than we want. And thanks to the fact that there's a little cursor, you can see how it looks like it's a little bit more negative than -1 is where the turning point actually is. So let's zoom in really close. Looks like it's somewhere between -1 and -1.2. So I'm going to use that as my viewing window. No, I'm going to use a different viewing window. Cool. So using that viewing window, where does it seem approximately like that turning point actually lies? say rounded to the nearest tenth.
-1.2.
-1.2? And I think that's good enough for now. How could you get, say, a better estimate now? Could you zoom in again?
Yeah.
Yeah. I definitely know that it's somewhere between -1.2 and -1.1. Oh, I know what I did. And there, now you get better information. You can get information as good as you want by repeatedly zooming in, taking local pictures. And I know this isn't up to the hundredths. That idea seem pretty okay? If you have access to a computer, you can use it. And that's really useful if you just want to approximate things. So what's one way to use a computer? Well, on the one hand, maybe you have a maximum button. I'll advocate a different strategy. I'll advocate the strategy of just zoom in until you have information that's as precise as you need. There's another strategy that comes from tools from calculus, in which you can reduce the idea of finding turning points to solving algebraic equations. This is calculus class. So, the last thing I want to hit today, anyway, is just a few local properties of functions. So I think I'm going to change this. I'm going to emphasize that these are solid dots on either side. So if you saw a function with this graph, and I asked you to maximize it, well, what does it look like the maximum value this function takes is? What is the biggest output you see?
5.
5. Because y values are outputs. On this graph, what is the biggest y value you see? 5. So the maximum value, I guess that I'm jumping around a little bit, the maximum value f takes is 5. What x value produces that maximum value?
-5.
Yeah. Yeah, you just look for the x value that corresponds to that y value. And I got myself confused because there's a typo in the notes. Replace that maximum with minimum. Let's minimize. So what is the minimum value that this function takes? What is the smallest function value you see on this graph?
-4.
-4. What x value produces it?
2.
2. So there's the most negative y value I see. It corresponds to an x value of -2. Now let's talk about local properties. So whenever I say a function is locally anything, what I'll be saying is if you zoom in really, really close to that point, does this function look like it has that property? So let's suppose I asked you whether x equals -4 produced a local max. Here's what I'm asking you. I'm asking you if you zoom in really, really close on that point, at that point on the graph, if you only saw this much of a graph, would you say that looks like a maximum value?
No.
No. Why not?
It just looks like a line.
Just looks like a line. Or y values that are bigger than it? looking at this graph, what x values would you say do look like they produce a local max?
0.
X equals 0 seems to. And as big a fan I am of that bit of shtick, I don't think anything is gained by me zooming in really, really close. You know what you're going to see. So there's a local max. So what values of x locally maximize? Well, it looks like x equals 0 does the trick. What values seem to locally minimize?
X equals 2 and x equals -3.
Yeah. And I'm about out of time, so I'm going to stop there for today. We'll pick this up next time.